Good morning, everyone. We are excited to present our final project titled Solving the 8 Puzzle Problem Using Search Algorithms. Our team members are Ahmed Omar, Gautam, and myself, Ishika. The 8 puzzle is a classic problem involving a 3 into 3 grid with 8 number tiles and 1 blank space. The objective is to rearrange the tiles to reach a goal state using the fewest or lowest moves possible. Our goal was to explore various search algorithms and determine the most effective way to solve this puzzle. And we aim to showcase the real world application of search techniques and heuristics, helping us build a deeper understanding of problem solving. Our main objective for this project were first to implement and compare different search algorithms, to design and apply effective heuristic, and finally to evaluate these algorithms based on performances like optimality, time taken, and computational cost. So here we used 4 search algorithms in our implementation. The first one is breadth first search BFS that basically explores the shallowest nodes first and guarantees the shortest path, but it is memory intensive. Second is depth first search DFS that dives deep into branches, which is memory efficient but can miss the optimal path. Third is uniform cost search that basically always expands the lowest cost node regardless of the depth. And finally, we have A star search that combines the cost to reach a node and the estimated cost to reach the goal using a heuristic, making it both efficient as well as optimal. Next up, we have approach. So our main approach involve implementing all 4 of the algorithms in Python. We use search strategies to explore possible tile movements and compare their efficiency in solving the puzzle. And by analyzing the outputs, we could determine which algorithm performed best in terms of both time and the solution quality as well. So our project solves the 8 puzzle problem using different search algorithms by simulating all the possible ways the tiles can be moved until we reach the final or the goal state. We implemented this using Python where each puzzle configuration is treated as a state, and the algorithms that we used, that is BFS, DFS, uniform cost search, and A star, all these explore these states differently. For example, BFS looks at all options layer by layer, whereas DFS dives deep into one path before backtracking. UCS also picks the lowest cost path, and whereas A star does the smartest search by combining cost and heuristic of how far the goal is. So basically, each algorithms maintain a list of puzzle states it needs to explore next and updates them as it progresses and stops when the final or the goal state is reached. We also use the Manhattan distance as our heuristic for A star, which helped guide the search more efficiently. While building this project, we encountered a few major challenges. A few of them are listed. For example, handling unsolvable states. So we had to implement a function to check whether a given puzzle is solvable before running any algorithm. And to find optimal solution and performance, for example, BFS gives an optimal solution but can be extremely slow or memory heavy on complex inputs, whereas on the other hand, DFS is fast but not guaranteed to find the best path. Balancing speed and optimal solution both was a bit tricky. And debugging recursive and priority logic, we while implementing UCS and A star, we involve working with Python's heap queue model to manage priority queues. So understanding how to maintain the right order of exploration was a learning curve. These challenges basically pushed us to understand the algorithm at a deeper level and also improved our debugging and coding practices. Throughout this project, we learned a lot. We gained a deeper understanding of how informed search algorithms work, and we saw firsthand how powerful heuristic can be in guiding search processes. And most importantly, we developed cleaner and testable Python code, improving our overall coding practices. To conclude, we successfully implemented and compared four search algorithms for solving the 8 puzzle problem, and among them, A star search stood out as the most efficient due to its use of heuristics. This project helped us appreciate the practical power of AI techniques in solving complex and real world problems. Thank you so much for your time and attention.
I'm Gautam Chebrolu. Now I'm going to explain you about the search algorithms which I used in the 8 puzzle solver. So we used four different search algorithms to find a solution path from a scrambled puzzle to the goal state. So first I'm going to explain you about breadth first search. So it's basically it explores all possible moves level by level, and it's always find a shortest solution, but sometimes it's slow and it uses a lot of memory. So coming to the code, if you see def bfs start goal, so q equal to dq start. So here it starts to explore states, and it tracks visitor states to avoid loops, and it expands nodes in level order, add new states to the back of the queue. And here in the code, if we go to the while loop, it pops the oldest state and check if it's the goal, and if not, it adds valid neighbor states to the queue. So coming to the second or such method, DFS, so it goes deep into the puzzle path before backtracking. Use less memory, but may miss the shortest part. But our goal is to find the shortest part, right? So here in the DFS code, it always uses a stack instead of a queue. It always explores deepest path first. Here, and it can go very deep before backtracking. Now coming to the UCS, so uniform cost search like BFS but considers the cost. It's like BFS but consider the cost to reach each state. So it uses periodic queue to expand the cheapest path. Good when we have most different costs, even though here all moves cost is one in our project. So coming to the code for the UCS, so it uses a priority queue to choose the lowest cost state. So here 0 is the starting cost. For every new move, cost is incremented by 1. So here it pushes new states with their cost, expand the state with smallest total path so far. So coming to the A star algorithm, in it's our most efficient algorithm. So here in we used Historic we used Hamming distance and Manhattan distance. So in Hamming distance, it counts how many tiles are in the wrong spot. Example, if 3 tiles are in wrong position, h of n equal to 3. It's simple but not very accurate. And the second distance, it's Manhattan distance. It adds up the number of moves each tile is away from where it should be. More accurate and informative than Hamming, leads to faster solutions with fewer expanded steps. So why A star plus heuristic work best? So A star with Manhattan distance finds the goal faster and explores fewer states. It's like both optimal and efficient. So in these four algorithms, A star outperformed the BFS, DFS, and UCS by a large margin. So coming to the code for A star, It uses a heap just like UCS. It adds a historic value on top of its cost. F of n equal to g of n plus h of n. G of n is nothing but cost to reach this state. H of n is nothing but estimated cost to goal. So in having distance, we count how many tails are not in correct position, as I told you earlier. So in algorithms.py file, we implemented the logic for BFS, DFS, UCS, and A star. A star was the most effective because it used a periodic queue and smart heuristic. We implemented both Hamming and Manhattan distance. Manhattan gave better results because it measures how far tiles are from the correct positions, guiding A star more efficiently. So now from here on, Omar will continue.
Hi everyone, I am Ahmed Omar Selim Adnan and I will be explaining the visualization part of our project. So this is the puzzle visualizer um, class which animates the solution path of the 8 puzzle problem using matplotlib. In the init method, we take the list of puzzle states and prepare the plotting area using subplots. We also adjust spacing for a clean layout. The draw state method draws a single 3 by 3 puzzle grid. Each tile is colored sky blue and the blank tile representing by 0 is shown as light gray. We draw rectangles and add numbers for visible tiles. The animate method is called for each frame of the animation, simply updating the puzzle to the next state using draw state. Finally, show method triggers the animation using func animation method, which with each frame shown every second. This makes the puzzle solution easy to visualize step by step. In the main file, we just simply build a CLI so that the our app is interactable by the user. So now I will show a demo. So if I open a new terminal and I just run python main.py, the main file, you can see the user can gets to choose one of the two start states. We could add more, but we just made two for now. And for example, let's go with the second start state. The goal state is over here, which is 1 2 3 4 5 6 7 8 in a clockwise position. Now the user is prompted to choose a search algorithm, so we will go with, let's go with a star search. So unlike the other searches, for a star search we also get to choose a heuristic. So let's go with Manhattan distance, and here we have an animation to so that we can visualize how the problem is getting solved, and it's already got solved. Let's select a different option this time. So let's start with the start state of 1, and this time let's go with depth first search, DFS, and let's see how our program performs. So it is not being able to find a solution, but let's go with um, a star again. So the first state, and this time is a star search, and let's go with Manhattan. So we can see that it has already found a solution for this state also. So not all algorithms are able to solve every possible problems. So this is let's wait for it to end. Yeah, so we have reached our goal state. So this